You know how video games can have these incredibly realistic physics? Or how your weather app can actually predict a storm pretty accurately? Well, the secret isn't some kind of perfect, flawless math. It's actually the art of the good enough answer. And trust me, this clever idea is quietly running, well, pretty much our entire modern world.
All right, so let's kick things off with a bit of a puzzle. Think about this. What do the physics in your favorite video game, the weather forecast you glanced at this morning, and, those super complex models trying to predict the stock market, what do they all have in common?
Okay, the answer might surprise you. They all run on calculations that aren't perfect. They rely on math that's good enough. And I know what you're thinking. Good enough sounds like settling for less, right? But it's not. Not at all. It's actually a brilliant shortcut to solve problems that would otherwise be completely impossible.
Now, to really get why good enough is such a game changer, we kind of have to take a step back and remember the world of perfect math.
Think back to algebra class, right? Every single problem had that one perfect, clean answer. X equals 5. Done. That's the world of what we call analytical solutions, where you can solve an equation perfectly on paper. But, as you've probably figured out, the real world, it's just not that clean.
Yeah, the real world is messy. It's rarely neat and tidy.
In science, in engineering, you hit these roadblocks all the time. Sometimes the equation you're working with is just monstrously complex. You just can't solve it perfectly. And this happens a lot, maybe you don't even have an equation to begin with. All you've got is a bunch of measurements, a series of data points from an experiment.
So that's the big question, right? If the perfect math from the textbook doesn't work, what's plan B? Do we just throw our hands up and go home? No way. We get smart. We find a way to get an answer that's close enough. We approximate.
Okay, so let's dive into the toolkit. Our first tool is all about answering a really basic question. How fast is something changing at any given moment?
In calculus, this is called finding the derivative. It's like finding the exact perfect slope at one tiny point on a nice, smooth curve. But what if you don't have that nice curve? What if all you have are these scattered red dots? Just a bunch of measurements. That perfect, clean answer, it's just gone.
And this is exactly where something called numerical differentiation saves the day. Instead of trying to find the perfect slope at one point, we just estimate it. We do it by looking at the points nearby. It's a really practical and powerful workaround.
And the basic idea is so simple, it's almost beautiful. You just pick the point you care about, then you grab another point that's really, really close to it, and then you just calculate the rise over run between those 2 points. Yeah, the same rise over run from middle school math. That little straight line you just made, that's your good enough guess for the slope right there.
So the big question is, how good enough are we talking here? Well, check this out. For this particular problem, the actual perfect answer for the slope is 22.167 and change. Using one of these approximation methods, we get 22.228. I mean, wow, that is incredibly close. And for pretty much any real-world job, it's absolutely perfect.
All right, so we've got a handle on figuring out rates of change. But what about the flip side? What if, instead of the slope at one point, you need the total area under an entire curve? Just imagine trying to find the area of a shape with this crazy wiggly top. You can't just do length times width, right? That's the classic problem of integration. And the solution, again, is so clever. Instead of trying to measure that weird, curvy shape all at once, you just chop it up. You draw straight lines between your data points, and what do you get? A bunch of simple little trapezoids. And hey, we all know how to find the area of a trapezoid. This is called the trapezoidal rule. You just break that impossible area into a bunch of easy little pieces, calculate their areas, and add them all up. And the best part, the more little trapezoids you use, the closer and closer you get to the real, perfect answer. But, we can always get smarter about this. Straight lines are a good approximation, but there are even more efficient and precise methods. So, the trapezoidal rule is great. It's simple, reliable, and uses points that are spaced out evenly. But then you've got something like Gaussian quadrature. Now, this is next-level stuff. It basically recognizes that some parts of the curve are more important than others. So instead of just taking samples at even intervals, it strategically picks the best points to measure. It's like, instead of pulling 1,000 random people, you pull the 20 most influential ones. You get a way more accurate answer with way less effort. It is literally the definition of working smarter, not harder.
So this brings us full circle. Why does any of this abstract math actually matter?
Well, it's because of this simple fact. In the real world, an answer that's 99.9% correct
that you can have right now is a million times more useful than a 100% perfect answer that's impossible to get or would take you centuries to figure out.
I mean, seriously, these good enough methods are the hidden engine running our entire world. Think about it. When engineers test a new airplane wing in a computer simulation, that's approximation. The physics in that video game, all approximation. Forecasting the weather, predicting the stock market, training an AI, every single one of these things relies on the art of being strategically, brilliantly good enough.
And the source material for this explainer really nails it. It says these techniques are essential, where analytical solutions may be difficult or impossible to obtain. And that's it right there. This isn't second-best math. It's the bridge that connects pure theoretical ideas to the messy, practical world we actually live in.
So, I'll leave you with this question to chew on. We're living in a world that is just drowning in data, right? It's getting more complex every single day. So, is the most important skill really about finding that one single perfect answer? Or is it about mastering the art of finding the best possible one?